We now move on to Chapter 10, Section 5 of our book, and we're going to be looking at a different aspect of the ideal gas law. And this different aspect of the ideal gas law looks at molecular weight, and it takes in density into consideration. So let's read this problem. A sample of a gaseous substance at 25 degrees Celsius and 0.862 atmospheres has a density of 2.26 grams per liter. What is the molecular weight of this substance? All right, I like this problem because a lot of times when people look at this, they think, wait, there's not enough information to solve this. And it turns out that there's plenty of information to solve this. The first thing that we need to consider here is what molecular weight is. Molar mass or molecular weight, either of those are fine. We typically talk about molar mass as the number of grams per mole. It's the mass of 1 mole. So one way we can think about that is that the molar mass, mm, is equal to m, which is the mass, divided by n, which is the number of moles. Well, now let's look at the ideal gas law, PV equals nRT. If we look at those two equations, there's one variable that they have in common, and that is the number of moles. So if we take that equation and solve it for n, we'll get this. And we've done this before. We did this on the previous set of problems where we looked at the number of moles. So PV over RT is equal to n, the number of moles. All right, well now we're going to take PV over RT and put it in place of n. So when we do that, we get molar mass is equal to mRT over PV. So again, PV over RT was in place of the n. And again, looking at that, you may think, well, now we've got 5 variables in a constant rather than 4 variables in a constant, so how is that better? Well, mass over volume, that's the density. So if we just kind of separate that out, make that mass over volume, we'll get the density. And so molar mass is equal to density times R times T over P. So there's the temperature, there's the pressure, there's the density, and R is a constant. So if we just put the values in, our density is in grams per liter. All right, so 2.26 grams per liter. R is our gas constant. Again, 0.0821 liter atmospheres per mole Kelvin. Temperature, we do need to convert to Kelvin. That's still true at 298. And then our pressure was given in atmospheres conveniently. So 0.862 atmosphere goes in there. And now we can cancel out some units. So we'll see liters cancels out, atmospheres cancels out, and Kelvin cancels out. It leaves us with grams per mole, which that happens to be the units for molar mass. So our molar mass in this case is going to come out to 64.1 grams per mole. So we can calculate the molar mass. Now, if we're given enough information in this, we can calculate any of these quantities, or including the density if enough information is given. So let's switch over to number 47. All right, so here on number 47, the very first part says calculate the density of NO2 gas at 0.970 atmospheres and 35 degrees Celsius. All right, so the quantity that we are looking for here is the density. So if we write out our equation, that molar mass is equal to dRT over the pressure, and then we solve that equation for density. So density, we'll cross multiply the P there, and then we'll divide by RT. So we'll get pressure times the molar mass over RT. That will give us the density. Okay, so density, our pressure is given as 0.970 atmospheres, and I am going to write all the units in. All right, our molar mass is for NO2 And so for NO2, let's go ahead and put that in. So 14.01 for the nitrogen plus 2 times 16, so 32.00 for the oxygen, and that gives us 46.01. So I'm going to put 46.01 grams per mole. And I'm going to drop the units of moles down in the denominator. All right, let's go ahead and put, we'll put T down here. Since it's 35 plus 273 comes out to 308, yes. So 308 Kelvin. All right, and then we'll put in, we've taken P, M, and R, and so now we just need to put in the gas constant at 0.0821 liter atmospheres per mole Kelvin. All right, we're going to check our units here to make sure things cancel out properly. Atmospheres cancels out, moles cancels out, and Kelvin cancels out. And what that leaves us with is grams per liter. So that leaves us with grams per liter. So let's go ahead and do the calculation. So 0.970 times 46.01 divided by 308. And then we also need to divide by 0.0821. And that gives us we've got 3 sig figs, so we're going to call that 1.76 grams per liter. And so that gives us our density. So that's pretty easy to do. All right, here we want to calculate the molar mass, so we're going to use this equation just as it is written. So molar mass is equal to dRT over the pressure. Density, if we look, we don't have density specifically stated, but we do have the mass and the volume. So we could put mass RT over VP, right? So density we just turned into mass over volume. Okay, so now we can put those numbers in. For the mass, we have 2.50 grams. And for our volume, we have 0.875 liters. All right, for R, let's go ahead and put R in, 0.0821 liter atmospheres per mole Kelvin. And then for the temperature, so temperature is 35 is 308 Kelvin. We just did that. And then our pressure is 685 torr. All right, so we've got one additional little calculation that we need to do, and that is to convert these torr into atmospheres. And we know that 760 torr is equal to 1 atmosphere. So now let's go through and cancel out things that can cancel out. So liters cancels out. Atmospheres cancels out, torr cancels out, Kelvin cancels out, and we're going to be left with grams per mole. And that's convenient because that is the typical units that we have for molar mass. So 2.50 times, I'm just going to multiply everything on top, so times 0.0821 times 308 times 760, and then we'll divide by 0.875 liters. And then we'll do one other thing is to take care of this 685. So divide by 685 torr. And that gives us, with 3 sig figs, that gives us 80.2. So we'll put 80.2 grams per mole. And that is going to be our molar mass of that particular gas. So we don't know what that gas is, but since we now know the molar mass of it, that will give us more information. Okay, so We now want to look at our next section, which talks about Dalton's law of partial pressures. And if you're wondering, yes, it's the same Dalton that we saw with Dalton's atomic theory. Dalton was a busy man. He did lots of stuff. So Dalton's law of partial pressures was, here is just a statement of Dalton's law of partial pressures. The total pressure of a mixture of gases equals the sum of the pressures that each would exert if each were present alone. All right. What that means is that if you have a bunch of gases, that the sum of the total gas, the sum of the total pressure, the total pressure is equal to the sum of all the partial pressures. One way of writing that mathematically that makes sense is, say, the total pressure is equal to the partial pressure of component 1 plus the partial pressure of component 2, 3, 4, so on and so forth. And another way of saying that makes it sound kind of obvious is that the total pressure is equal to the sum of its parts. Now, in and of itself, this is pretty cool and pretty useful, but what's really useful about this is that if this is true, which it appears to be true, then we can write ideal gas laws for each of the gases individually. We can treat them as individual components. We don't have to solve the whole thing and subtract off all the other stuff. We can just look at each individual component. And that is a really, really useful tool. Now, there is another thing that we look at that is called the mole fraction. And the mole fraction of a component in a mixture is the total number of the number of moles of the component divided by the total number of moles. It's not a percentage, it is a fraction. And so we'll use the Greek letter chi, you can just call it x if you want, that tells us how much of that component it is. Well, it's going to be the number of moles of that component divided by the total number of moles. Now, because Dalton's law of partial pressures is true, if you have a mixture of gases, then you can write this, that for a gas, the mole fraction is simply the ratio of the partial pressures of the component to the total pressure of the gases. And so the mole fraction is partial pressure of 1 divided by a total pressure. And this would only work if Dalton's law of partial pressures is true, which it appears to be true. Now, how we use partial pressures is that we can subtract away certain, like the partial pressure of one component to get the partial pressure of a different component. And for example, one of the things that we like to do is that sometimes we will collect a gas over a liquid, and usually water is a convenient one to do this with. But in the process of doing this, so we're producing this gas and these gas molecules bubble through the water. Well, the gas is going to pick up some of those water molecules so that we have water vapor present in this container up here. So if you collect a gas over the water vapor is mixed in there. So the total pressure is equal to the partial pressure of the water vapor plus the pressure of whatever the gas is. If you want to get the pressure of the gas, then you need to subtract away the partial pressure of the water. And that partial pressure is simply going to be the vapor pressure. We'll talk about vapor pressure in the second semester, but it's a temperature-dependent number that we're interested in. So we want to go back and look at number 52. We'll do 52, 58, and 61 here. So we're going to go back. All right, so here we've got calcium hydride. I think we saw this reaction in chapter 3, but it reacts with water to form hydrogen gas. And here we go. We've got calcium hydride plus water gives us calcium hydroxide plus hydrogen gas. And it's a really, really useful reaction for producing hydrogen on the go. If you want some hydrogen gas quickly, but you don't want, a big explosion, this is at least a pretty good start for it. All right, so how many grams of calcium hydride are needed to generate 53.5 liters of hydrogen gas? Well, what we're going to need to do is we're going to do a roadmap. because with this information, we can determine the number of moles of hydrogen gas. And from the number of moles of hydrogen gas, we can convert to the moles of calcium hydride. And from the moles of calcium hydride, we can get the mass of calcium hydride. But in order to do this, we first need to get the number of moles of hydrogen. Well, what Dalton's law of partial pressures tells us, right? We know that the ideal gas law is this. It's that PV equals nRT. Well, what Dalton's law of partial pressures tells us is that the partial pressure of a component, and I'm just going to call it hydrogen at this point, times the volume is equal to the number of moles of that component, hydrogen, times RT. So we can solve that equation for the number of moles of hydrogen. So our number of moles of hydrogen is going to be the partial pressure of hydrogen times the volume over RT. All right, so our partial pressure of hydrogen is 814 torr. Now, we will need to convert that into atmospheres, but that's no big deal. Let's see, volume. Our volume here is 53.5 liters. The temperature is 21 degrees Celsius, so 21 plus 273 is 294 Kelvin. And then here we'll put R 0.0821 liter atmospheres per mole Kelvin. And then we'll put 1 ATM over 760 torr. And that will convert us so that we're all in the right units here. So we're looking for number of moles. Let's cancel things out. So torr cancels out, atmospheres cancels out, Kelvin cancels out, and liters cancels out. And the moles that we get here will be the moles of hydrogen. So that gives us 2.3. Well, here, I've got that number, but let's go ahead and do the calculation here. So 814 times 53.5 divided by 294, and then divide by 0.0821, and then we'll divide by 760. And we get 2.373. And I'm just going to put 2.374 moles. Now, technically, we only have 3 sig figs, but I'm going to round after the next step. So, okay. So now that we have that, we have moles. So 2.374 moles of hydrogen. Moles to moles ratio, and the ratio here is the ratio in the balanced equation, and we want the ratio of calcium hydride to hydrogen, so that's going to be 1 mole of calcium hydride for every 2 moles of hydrogen gas. And then moles to mass, we'll use the molar mass, and I figured out this molar mass a little bit earlier, 42.10 grams of calcium hydride per mole of calcium hydride. If you look, moles of hydrogen cancels out, moles of calcium hydride cancels out, and that's going to give us our grams of calcium hydride. So 2.374 times 42.10, and then we'll divide that by 2. And you'll see we get 49.97. We have 3 sig figs, so we're going to call that 50.0 grams of calcium hydride. Again, we have 3 sig figs from up here. I just carried through all the numbers. All right, so we get 50.0 grams of calcium hydride. So for a little under 2 ounces of calcium hydride, you mix it with some water, and you end up getting 53.5 liters of gas, so you can fill your life raft, which that is pretty convenient. Okay. So now what we want to do is we want to look at number 58. All right. And it says, consider a mixture of two gases, A and B. A quantity of a third gas is added to the same vessel at the same temperature. How does the addition of gas C affect the following? All right, so there's a couple of things. Let's draw a picture of what's going on here. So we've got a container here. I'm just going to make it a square container. And to start with, we've got gas A, which I'll call partial pressure of A, and gas B, which is partial pressure of B. And then we're going to come along and add a third gas, and I'm going to put it in red, so I'll put plus partial pressure of C. So at the beginning, the total pressure was equal to partial pressure of A plus partial pressure of B. But after we added the gas, we're going to add partial pressure of C. Now, in terms of what the partial pressure of A is, the partial pressure of A is going to be equal to the number of moles of A times RT over the volume. So when we add gas C, it doesn't affect the number of moles of A. It doesn't affect the gas constant, because that's a constant. It doesn't affect the temperature, because we're doing it at the same temperature. And it doesn't affect the volume of the container. Remember, the volume of a gas is small compared to the volume of a container. Or the volume of the molecules is very small. So the volume is not affected. So that means that the partial pressure of A, there's no effect on the partial pressure of A. The total pressure of the vessel, that one's pretty obvious. Because the total pressure is equal to the partial pressure of A plus the partial pressure of B plus the partial pressure of C, when we add gas C, we're going to increase. So P total increases. All right. And then finally, the mole fraction of B. Well, the mole fraction of B is going to be equal to the number of moles of B divided by the number of moles total. Now, we could have done this in terms of partial pressures as well, but the number of moles of B will be unaffected by adding gas C. But the total number of moles will be increased because we're adding a different gas in there. So if we add a gas and we're increasing that number in the denominator, that means that the mole fraction of B decreases. Okay. So on this, on number 61, we got a piece of solid carbon dioxide with a mass of, solid carbon dioxide, by the way, that's dry ice, with a mass of 5.50 grams is placed in a 10-liter vessel that already contains air at 705 torr and 24 degrees Celsius. After the carbon dioxide is totally vaporized, what is the partial pressure of carbon dioxide and the total pressure in the container at 24 degrees Celsius? All right, so there's two things we're looking for. We're looking for partial pressure of CO2 and P total. Now, it doesn't specify what units we should put those in, so I'm going to just solve them for atmospheres. All right, let's start with the partial pressure of CO2. Our partial pressure of CO2 is equal to the number of moles of CO2 times RT over V. Again, Dalton's law of partial pressures allows us to just use the ideal gas law and put that component in. Well, we don't know the number of moles of CO2, but we do have the mass, and we can convert from mass to moles using the molar mass. So I'm going to put in 5.50 grams of CO2, and then we'll divide by the molar mass. And I happen to remember that the molar mass of CO2 is 44.01 grams of CO2 per mole of CO2. All right. R is 0.0821 liter atmospheres per mole Kelvin. And then temperature, the temperature is 24. 24 plus 273 is 297 Kelvin. And then the volume is 10 liters. So we'll put 10.0 liters. All right, and if we go through and check, let's check our units here. So our grams of CO2 cancels out, our moles cancels out, liters cancels out, and Kelvin cancels out. It's going to leave us with our answer in atmospheres. So our partial pressure of CO2, when we do that calculation, clear all that, so 5.50 divided by 44.01, enter, times 0.0821 times 297, and then we'll divide by 10.0. And you'll see the number that we get there is 0.304. So 0.30430, we'll call that 305 because we should round that to 5. Atmospheres. So our partial pressure of CO2 is equal to that. All right, well, our P total is equal to the partial pressure of air plus the partial pressure of CO2. And so we're going to go ahead and convert and get that partial pressure of air. Our partial pressure of air is equal to 705 torr. And then we'll put 760 torr is 1 atmosphere. And we get 705 divided by 760. And you'll see we'll get 0.928. So 0.928 atmospheres is our partial pressure of air. So now our total pressure, and I'm going to put this in a different color, P total is going to be the partial pressure of air, which is 0.928 atm, plus the partial pressure of our carbon dioxide, which is 0.305 atm. And 0.928 plus 0.305 gives us 1.233 atmospheres. And that'll be our total pressure. I do like to work this out and show it to you for sig fig purposes. This goes out to the thousandths place. Even though they each had 3 sig figs, our answer has 4 because, again, we're going out to the thousandths place when we're doing addition. Okay, so there we go. That is Dalton's law of partial pressures. We're going to switch back over here. Okay, I turned off my microphone there for a second because I was moving my microphone around. All right, so now we want to look at this last section, which is talking about kinetic molecular theory. And kinetic molecular theory is a theory that helps us to understand gases. It's the theory of moving molecules. We know that our molecules are constantly moving around. So the kinetic molecular theory tells us, first of all, why gases obey the gas laws. But also, kinetic molecular theory gives us information about why some gases don't exactly obey the gas laws. So why we get deviations from the gas laws. And there is a logical reason behind it. So first of all, we're going to look at the tenets of kinetic molecular theory. All right, here, let's see. So this theory tells us that the pressure in a container is the force of the molecules colliding with the walls of the container divided by the surface area. Okay, so if you look over here, you'll see a picture of molecules. The molecules are running into the wall. Every time a molecule runs into a surface, it exerts a force on that wall. If you take all of those forces and divide by the area, then you'll get the pressure. And so that's what pressure is. Atmospheric pressure is the same thing, except it's the weight of all those molecules, and as they run into stuff, it's the weight divided by the area over which they are exerted. So the main tenets of kinetic molecular theory are this. First of all, that gases consist of large number of molecules that are in constant random motion. And there's a lot that's built into this. A large number of molecules means it's almost an uncountably large number of molecules. If we have Avogadro's number of molecules, we never would have time to count all of those particles. The constant means that it's constantly moving, so the molecules are always in motion. They never stop. They never come to a complete stop. And the random means that they're going in all different directions and that they're going at more than one speed. The molecules, there's a broad distribution of the speeds of the molecules, and I'll show you a graph that demonstrates this a little bit later. All right. The combined volume of all the molecules of a gas is negligible relative to the total volume of the gas. If you imagine for a moment that you've got a large container of a gas, let's say a liter. Well, if you took all the molecules that made up that gas and compressed it down so it became a liquid or a solid, you would find that the volume of that liquid or solid would be much, much smaller than the volume of the gas. And that's because gas molecules are very far apart relative to their size. So that size of the actual molecules, if you add the little bit of size of each of the individual molecules all together, that's going to be a very small number compared to the total volume of your container. And that's what this is saying, is that we can kind of ignore the fact that molecules have some size. Kind of. 3, attractive and repulsive forces between the molecules of a gas are negligible. And what this says is that there are attractive forces between molecules that are mostly exhibited in liquids and solids. We don't see them as much. We don't see these intermolecular forces as much in a gas. And so we're going to say that in a gas, these attractive and repulsive forces are negligible. If you go to chapter 11, the very first thing that we'll see is that for liquids and solids, they're very important. And that chapter 11 is all about intermolecular forces. But for gases, we're mostly going to neglect these intermolecular forces. The fourth thing, collisions between molecules are elastic. And elastic means something different in science than it does in like everyday life. Elastic, like we would think of elastic as like a rubber band is elastic. But in science, when we're talking about collisions and we say collisions are elastic, we're saying that when two objects collide, they don't lose any kinetic energy. So all of the kinetic energy is going to be conserved. What this means in terms of molecules is, well, if two molecules or a million molecules, it doesn't matter how many, but when you have molecules and they run into each other, all of the kinetic energy is conserved. Now, it may be converted from translational to rotational, and again, I'm not going to get into that in any great detail, other than to say that this is pretty much true. Now, what's not true is if you have collisions of macroscopic objects like like tennis balls. If two tennis balls run into each other, you lose some of the kinetic energy to friction because the ball heats up and stuff. But for molecules, the fact that they are moving, well, that is heat. That is what you would get from friction. So this fourth assumption is pretty good. Our fifth assumption, the average kinetic energy of the gas molecules is proportional to the absolute temperature of the sample. And what this says is if we double the kinetic energy, we're going to double the temperature. So if we double the kinetic energy, the average kinetic energy, we're going to double the temperature. Okay, so those are our main tenets of kinetic molecular theory. They are mostly true. 4 and 5 are definitely true. 2 and 3, there are some weird exceptions, and when these are not quite perfect, that's when we start getting deviations from the ideal gas law. So let's look at how fast do the molecules actually move. Well, the answer to that question depends largely on what do you mean by how fast? What do you mean by speed? And so there's a couple of different speeds that we can measure, and it turns out one of them is going to be much better for our calculations. So there are different kinds of average speed. One is called the most probable speed. In statistics, we would think of this as the mode, right? What speed are more molecules moving at any given time? So it's the most probable, and it's going to be the top of this peak. If we look at this, we'll see a distribution of the different speeds of a molecule in a sample, and we'll find that the top of that peak is going to be the most probable. The average speed is the mean speed. So if you were to add up all of the molecules, say, all right, what's the speed of every single molecule, and you had a really big calculator, and then you divided by the total number of molecules, you would get the average speed, the mean speed. And that would be an almost useful number, but it wouldn't quite be what we needed. We would need another bit of information, which is called the root mean square speed. And it turns out that the root mean square speed is going to give us the information we need relative to energy, the average kinetic energy, and it's also going to help us do our calculation. So root mean square speed is the one that we want. So let me explain what this graph is. This one is for nitrogen, and this is a sample of nitrogen that is at 0 degrees Celsius. And on the x-axis, we have the molecular speeds in meters per second. So it goes from 0 up to 1,000. All right, so there's 500 there. There's 1,000. So it goes up from 0 to 1,000 meters per second, which is pretty fast. And the y-axis is the fraction of molecules that have that particular energy. And we will find that, that the molecules... there are some molecules that are going very slow, but there's not very many of them. The higher this line is, the more molecules in that range are going to have that speed. At the top, that's where our most probable speed is. And then you'll see that the number of molecules as we go faster, it kind of diminishes. But because 0, we can't get less than 0. We have sort of a hard end here, but this, we can get quite a few. It tails off. We get quite a few molecules that are going much faster. And that's why we get stuff like a root mean square speed and average speed that we need to take into account. Okay, all that said, we're interested in the root mean square speed, the RMS speed. All right, and this is, like I said, for nitrogen at 0 degrees Celsius. Well, let's look at a different gas. Let's look at gases of different sizes. All right, and so we'll find, if we have a sample of a mixture of gases, let's say all of these gases are mixed together, and they're all at 25 degrees Celsius. Well, if the temperature of the sample is at 25 degrees Celsius, all of the individual components are also at 25 degrees Celsius. So they all have the same average kinetic energy. However, because they all have the same average kinetic energy, in order for that to work, smaller molecules have to be moving much faster than bigger molecules. So here we've got hydrogen and helium. They're very small molecules, and you'll see that they are moving much faster than our bigger molecules like oxygen and nitrogen. So we get a narrower distribution of speeds for the bigger molecules, and it tails off much faster. And then for the smaller molecules, we have a much broader distribution of speeds. We can write the formula for the RMS speed, and that RMS speed, the root mean square average, is going to be equal to the square root of 3RT over the molar mass. Well, so 3 is obviously, that's just a number. R is a constant. It's the gas constant. I will note that it's actually the 8.314 joules per mole Kelvin. In case you're trying to do a calculation, it's the 8.314 version of R. T is the temperature in Kelvin, and the molar mass, if you want to do this calculation, the molar mass is going to be in kilograms per mole. Now, I say all that. I don't think I have you do any of these on the homework. So that is our RMS speed. All right, so before we move on, I want to show you one of the implications of this. And I'm going to do that by showing you a cute video. And this is a cute video of some kids. All right. And I've been showing this video in class for a long time. All right, let's see if this works.
Hi, I'm Rosie. And I'm Anna. And we are going to be mad scientists. Everyone knows about helium. It's lighter than air. And if you put it in a balloon, it goes up.
Okay, I'm going to pause for a second. So while Rosie and Anna are adorable, they're not very good at exposition because they're not, they're not scientists yet. But that's okay. They're going to be mad scientists eventually. And since this was this was published on YouTube like 12 years ago, who knows? They may already be mad scientists. So what they're really saying is that because 1 mole of gas will take up the same volume regardless of what the gas is, gases with smaller molar masses are going to be less dense. So the density of helium is going to be much less than the density of air.
But some gases are heavier than air.
Okay, so here they do no exposition whatsoever. They have filled this large container with sulfur hexafluoride, SF6. And SF6 is quite large, and so it has a fairly high density. And then inside this balloon, they have air, and the air has a much lower density, and so the air is buoyant. It floats on top of the sulfur hexafluoride.
Ta-da!
Okay, so again, they don't really explain things here. They have filled their aquarium here with sulfur hexafluoride, and that sulfur hexafluoride, so it's more dense, so it'll stay in there. And then here they've got a boat that's made out of aluminum, and of course it has air in it. And watch, they're going to float that boat on the sulfur hexafluoride. This is cool. All right, now she's getting a beaker full, and she's pouring the sulfur hexafluoride into it. And look, it sinks the boat.
Hi.
Okay, so this is the part that I was interested in for talking about the average kinetic energy. The average kinetic energy of the helium in those balloons is the same as the average kinetic energy of the air around. However, since the helium is much smaller, the molecules move much, much faster. Since they move much, much faster, as that helium flows past your vocal cords, it compresses the sound vibrations and makes your voice sound squeaky.
I'm Rosie. And I'm Anna. And we have squeaky voices.
Okay, and conversely, if they take a very large molecule like sulfur hexafluoride, well, sulfur hexafluoride has a much higher density than regular air, and it also has a much slower speed. And so the molecules of sulfur hexafluoride, they go past their vocal cords much more slowly, and it stretches out those sounds. So by the time it hits your ear, it sounds really low voice. So here we go.
Crazy. You're crazy, man. I like you, but you're crazy. I love you.
All right, so a big shout out to Rosie and Anna, and also I guess big sister Hannah. Okay, so just a quick note about this. I'm sure you probably at some point have done the thing with the helium where you breathed in the helium from a helium balloon and it made your voice squeaky. That's fine. You can do that as long as you don't do it over and over again. And the reason I say don't do it over and over again is because to the extent that you're breathing helium, you are not breathing in oxygen, and you need oxygen in your lungs to get oxygen to your blood and to your brain. So if you're to breathe in helium constantly, you would eventually find yourself passed out and unconscious, and maybe even deprived of oxygen in your brain. For sulfur hexafluoride, it's a little bit more problematic, because with the sulfur hexafluoride, because it moves slowly, it takes a lot more time for the sulfur hexafluoride to diffuse out of your body. So I'm going to recommend not breathing in sulfur hexafluoride. Plus, SF6 is a very potent greenhouse gas, and no need to use more of that than we absolutely have to. Okay, so anyway, cute video, cute kids. Who knows where those kids are? Maybe they're professors by now, because that was 12 years ago. Who knows? All right, so next we want to look at effusion and diffusion, and these are related processes. Effusion is the escape of gas molecules through a small hole in into an evacuated space. So here, if we've got some pressure of gas here, and then over here we've got an evacuated space, and then there's a hole in between them, we will find that effusion is the process of those particles effusing through that hole into the vacuum. And we'll find that the rate that happens is going to be dictated by the size of the molecules and the speed of the molecules. Diffusion is the spread of a substance through a space or some other substance. And diffusion is something we experience all the time. Somebody puts on perfume across the room, and so molecules that are in the gas phase, they start to spread across the room, and eventually they get to your nose. Well, they have diffused to your nose. So that is diffusion. Now, we'll find that the molecules don't move just straight across. They move kind of in what we call a random walk, but we can predict how long it would take for molecules to get a certain distance. All right, so that's diffusion. So effusion and diffusion. Well, we have something that's called Graham's law of effusion and diffusion, and Graham's law tells us that the rate at which a gas effuses or diffuses is directly proportional to the root mean square speed of the gas. So in other words, the rate that one effuses to the divided by the rate that two effuses is directly proportional to the mass. The molar, is directly proportional to the speed that the molecules are moving. Well, we saw that the speed that the molecules were moving is inversely proportional to the molar mass. Now, with this equation, if we cancel out the 3RT, we're going to get this. So we'll get the rate of 1 divided by the rate of 2 is equal to the square root of the molar mass of 2 divided by the molar mass of 1. And that's kind of cool. So what this says is the lighter the molecule, the faster it effuses. All right? Or diffuses if we're looking at diffusion. Where this becomes a useful thing, and there's all kinds of applications of this, but where this becomes a useful thing is in uranium enrichment. That's one of the important applications of this is uranium enrichment. If you dig up uranium ore, so there's uranium, it's uranium oxide, you dig it up, you'll find that there are two isotopes of uranium. One is uranium-235, and it makes up about 1%. Okay, so uranium-235 makes up about 1% of naturally occurring uranium. And uranium-238 makes up about 99% of naturally occurring uranium. It's approximate. All right, so 1% and about 99%. Well, if you're going to use uranium for nuclear fuel in a nuclear reactor or nuclear power plant, that kind of thing, it's the uranium-235 that's the good stuff. It's the stuff that gives you all that energy. The uranium-238 will give you energy, but not nearly enough to power the nuclear reactor. So you need that uranium-235 to do the fission process in order to do that. Well, the problem is that chemically uranium-235 and uranium-238 are identical. There's essentially no difference in the chemical properties of those two isotopes. So what they do is they turn that into a gas. So they'll make uranium-6 fluoride or uranium hexafluoride for both of those gases, and they will do this thing of effusion. Now I'm going to show. We're going to do the calculation here for what would be the ratio of the rates of effusion. So the ratio of the rates of effusion is going to be, the rate of uranium-235 over the rate of uranium-238, and we've added in all the fluorine, so we need the molar mass of uranium-238 up here and the molar mass of uranium-235 down here, and I've calculated those numbers and put them in, and I'm going to go to calculator split screen. Let's see if we can do this. Okay, yes. We'll clear that, and we'll do the square root. So second, square root of 352.04 divided by 349.03, and then we'll close the parentheses, and we'll take that square root. And the number that we get there is 1.004. So 1.004. That means that the uranium-235 is going to effuse at about 0.4% faster than the uranium-238. And you may be wondering, okay, well, how do we take advantage of that? Well, let's go over here. So imagine that we've got a container here. This is our starting container. And in that container, we've got 1% uranium-235 hexafluoride and 99% uranium-238 hexafluoride. And in the next container, we've got an empty space, a vacuum, and then there's a tiny hole. Well, we'll find that the lighter molecules will effuse through that hole at about 0.4% faster. So about 0.4% faster. And so the concentration of uranium-235 will be higher in the second container than it will be in the first. Now, at 0.4% faster, we're not going to get a huge increase in the concentration. So once we do that, we're going to have to do it again. And again, and again, and again. And each time we're going to increase by about 0.4% the amount of the uranium-235. If you do that hundreds of times, then you can get a much higher concentration of the uranium-235. If you can get that uranium-235 up to a concentration of about 10%, then you should be able to start using it in a nuclear reactor. If you want to make a bomb, which I'm going to discourage you from doing, if you want to make a bomb out of it, you really need to get that uranium-235 percentage up over 90%, and the more pure, the better. Now, in case you're thinking, hey, I'm going to try this at home. No, you don't want to try it at home. One, the uranium hexafluoride, the UF6, is very, very reactive, and it's very, very dangerous to work with. And so if it comes in contact with the air, it hydrolyzes and gives off heat. So it essentially catches on fire and produces nasty toxic gases. So you have to have very specialized equipment to do this. And on top of that, it takes a lot of energy, a lot of electricity to set up this kind of facility. Now, if you're using this for a nuclear reactor, in the long run, you'll get a lot more electricity back out with the nuclear reactor than you would have used here. But this is a very expensive process. If you want to set up a facility that does this, you're probably going to spend many billions of dollars to do that. So it's very specialized, not something that you can do. And if you think you can maybe do it in your garage, you're going to be sadly mistaken. So, okay, so that is that. And I just like to mention that because it is a useful application of talking about uranium, or talking about effusion. All right, our last topic in this chapter is looking at real gases. So real gases. Real gases, this is where I say, oh, well, I've been sort of fibbing to you. There's no such thing as an ideal gas. Real gases are going to deviate from being ideal by a certain amount. It just depends on the conditions and everything. So an ideal gas, according to the PV equals nRT, if we put that into the equation at STP, we'll find that the volume of that ideal gas should be 22.41 liters. Well, here I've got the volume of these gases at standard temperature and pressure, and you'll see that they're somewhat different than 22.4. And there's a couple of reasons for this. One of the reasons is that these molecules don't have zero volume. So there's the volume of it, and also there are the attractive forces between the molecules. So we have to take those things into consideration when we're dealing with real gases. However, you'll notice that the numbers are pretty close to that ideal gas. They don't differ by more than, I don't know, like here about 2%. All right. And some of them are really, really close. Like helium is really close to being an ideal gas. So we want to know why it is that these gases don't behave like ideal gases. Why are they a little bit off? And why is helium so good? So I'm going to show you a graph that shows you how do real gases deviate from being ideal. Now to do this, we're going to take the ideal gas law, PV equals nRT, and we're going to solve it for n. And we're going to get the ratio PV over RT. So if I take a mole of a gas, 1 mole of a gas, and put it at 1 atmosphere, all right, and then take the ratio of PV over RT, I will get a number, and it should come out to 1. Well, when the gas is close to 1 atmosphere, less than 1 atmosphere, we'll find that most gases behave like ideal gases. They're really, really close to being an ideal gas. But as we increase the pressure, so here as we increase the pressure and go to higher pressures, we'll find that some of them will deviate, and that number, the PV over RT, will be less than 1. And for others, that number will be greater than 1. Well, the amount that it deviates depends on a couple of factors. So again, at low pressures, they act like ideal gases, but at high pressures, they can deviate quite a bit. And the amount they deviate is a big deal. So, okay, so that is how much do real gases deviate from ideal. Now, what makes real gases deviate from being ideal? Well, remember 2 of our assumptions. One was that the size of the molecules are small compared to the overall volume of the gas. And that's the molecules themselves are negligible. Well, as we go to higher pressure, we will find that the size of the molecule becomes more important, because the size of the molecule itself doesn't change, but as we go to higher pressure, the distances between the molecules will increase quite a bit. So at high pressures, we'll find that real gases start to deviate from being ideal. We'll also find that if we lower the temperature, so here we've got an ideal gas at some temperature, and then here, as we lower the temperature, we start to have these attractive forces. Well, if you remember, one of our tenets of kinetic molecular theory is that these attractive forces are negligible. Well, in some cases, as the attractive forces become stronger, that means that the molecule isn't moving with as much force when it hits the wall, which means that the pressure is going to be less. We'll find that these interactions become more important at low temperatures. So we'll find that the assumptions for kinetic molecular theory start to break down at high temperature and low pressure. So at high temperature and low pressure. So we're going to switch over to the last problem of the in-class assignment, number 69. And we want to look at what change or changes in the state of a gas bring about each of the following effects. And the changes that we can look at are changes in volume, changes in pressure, and changes in temperature. So let's see, the number of impacts per unit time on a given container wall increases. Again, if we kind of have this mental picture in our head that we've got molecules, and so here's a molecule and it runs into the wall. If we want to increase the number of times, the number of impacts that we get on that container wall, what things could we change? Well, if we decrease the volume, that would do it. So if we decrease the volume, then the molecules would run into the wall more often because they would be closer together. And if we increase the pressure, that would have the same effect. And then likewise, if we increase the temperature, the molecules will be going faster and they'll run into the wall more often. So increase temperature. So changing these three things will increase the number of times that molecules will impact the sidewall. All right. The average energy of impact of molecules with the wall of the container decreases. So this is how much energy does this individual molecule have when it hits the wall? Well, that is going to be dictated entirely by the temperature. So if we want to decrease the amount of energy, we just decrease the temperature. All right. The average distance between gas molecules increases. Well, this is something where temperature isn't going to help us out. If we increase the temperature, they're still going to be the same distance. They'll just be moving around faster. So the only things we can do here are to increase the volume or decrease the pressure. And then finally, the average speed of the molecules in the gas mixture is increased. Well, if you want to increase the speed of the molecules, then you need to increase the temperature. Okay, well, let's go back. I've got one more page that I want to show you. And to deal with real gases, we use something that's called the van der Waals equation. Now, you're not going to have to do calculations with the van der Waals equation in this class, but it is a way to make corrections for non-ideal behavior in real gases. So you remember the ideal gas law is PV equals nRT. Well, the van der Waals equation is this. And you know, usually if I show students this, they look at it and say, well, that looks really hard. Am I going to have to solve for n? And the answer is no, you're not going to have to solve for n, but it's not that bad even if you did. All right, so really what you have here are two correction terms. The first correction term is to the pressure, and that first correction term, the key component N and V, you're familiar with those. It's the A that we're interested in. That A is a correction factor that takes into account the attractive forces between the molecules. So for helium, the attractive forces are really weak, so we get a very small number. As we increase the size of the molecules, the intermolecular forces will increase, and so we get some pretty significant numbers with things like CO2 and carbon tetrachloride. So A is takes into account the attractive forces. B takes into account the size of the molecules, and so we subtract this term from the size, the volume, and that will give us an accounting for the size of the molecules. And so as this number gets larger, then the size of the molecule starts to become important. Now, these numbers are determined from experiment, and so these are what we call semi-empirical numbers. All right. Like I said, I just wanted to show you the van der Waals equation so that you're familiar with it and you understand that this is for attractive forces and this is for the size of the molecules. And that is the end of chapter 10. And so the next video that you want to be looking at is for chapter 5.